always like inviting people to join to our Discord. You can scan it and just join to ask some questions and say hi to everyone. Like it's a good place to ask some questions about ZK as well. And you can find my GitHub here. So yeah, elliptic curves. I will pass this immediately. Um, yeah. So as you can see here, we have different images of elliptic curves, and the elliptic curves constructed over finite fields are best friend, as I told you, because they provide us a cryptographic group, which the discrete logarithm is pretty hard, and we want this because we don't want people to solve our calculations easily with like I think it's like with force trying. So yeah, elliptic curves pretty good about it, and the most common form is Weierstrass. I don't know how to read it correctly, but I guess Weierstrass form. And you can see the formula here. We are using this formula, and if you change the A and B here, you will get different shape of elliptic curves. Um, so yeah, these are some examples as you saw, and the case we have to be careful about is the singularities. When you change A and B, you can get different results, right? So if your A is 0 and you satisfy this equation, which is 4A cube minus 27B square, like you will get cusp. So sorry for that. So you will get the cusp, and which has two same lines. They both have the same tangent. They have the same slope. So we don't want this. And the other one is not. And if your A is not 0 and you get the singularity, which you will have a single point that has two solutions, right? It will give you ambiguity. So they both are like security flaws. We don't want these. So we have to be careful about this formula, and like we always exclude this in our elliptic curve choices. So yeah. So yeah, let's talk about the fields, finite fields. It's a fundamental cryptographic component as well. It's a set of elements that has two binary operations, which is addition and multiplication. Like a good example of fields are real numbers. They have it's a uncountably many. It has uncountably many elements. That's why we call it a field. But if we strict it, we can say that it's a finite field, right? So yeah, let me show the next one. So when we yeah when we uh, at the first page, I told that we construct our elliptic curves over finite fields. So the first one we have to do is choosing a prime number, which will be our like big prime number, which will be our base field. Then we will choose these elliptic curves, and we will use both of them to satisfy these all like security things, the easy calculations, a lot of things going on back there. But yeah, we have to choose these two very carefully. And the when we choose this elliptic curve and the base field, the base field is our finite field. You can see that like in these four images, they have the same elliptic curves but different finite field, right? The different base field. So the first one, for example, is 19. You can see that it's the maximum number is 18. So you can't pass 18. It will wrap up to 0. You have different results. Each result is our elliptic curve. When you use that equation, you will get different results, and each point is your x and y coordinates. So you will get, I don't know, like maybe 15 results. And if you increase your finite field size, like moduli, you will get, for example, in the second one is 97, you will get more results. If you increase it to, I think this one was 127. Let me, yeah, 127. You will get more and more results, and 487. So they are all primes, and if you increase it, you will get more results. So I will talk about private key, public key calculations a little bit, and this is very important because these points will be your, for example, your public key in a point, and you don't want people to calculate backwards and find your private key, right? So that's why if you increase your size, you will get more results. That's why we are choosing, I don't know, like two over something crazy, like 256, 54, like a lot of bits. And it will be huge, like it's a very big number, and you cannot calculate the backwards, right? You cannot try force try. So yeah, why we are choosing prime number is another thing. This space field has to be prime because if it's not, you won't have multiplicative inverse for some numbers. For example, if you have mod 4, which is not prime, 2 has no multiplicative inverse, right? You cannot get 1, never, because it will be always even number, and you cannot get 1. That's why we want, it's if it was 5, for example, you can just say, okay, 3 times 2 is 6, and it's like equal to 1. So multiplicative inverse is 3. Yeah, that's why we have to be careful about it as well when we are choosing base field. So yeah, we will use this to get these results. Each dot here is our they will form a group. I will explain it in here. Let me be perfect like this. Okay, so a group is also a good like we have to have this property as well, and when we calculate this like finite field elliptic curve, we will get this result. Each dot are set, these sets will form a group in our elliptic curve, and they have only one operation, which is addition, and they have to the group. If we want to call a set a group, we have to be careful about these 5 properties. It has to respect like yeah, it should be respecting all of these, and you can see like for enclosure, we say that if A and B inside the set, the result should be inside the set. So you have 2 dots, your the other dot, your result should be inside your set as well. On your elliptic curve result, actually, like equation. So associativity says that in parentheses a plus b plus c should be equal to a plus b plus c. Identity says that we have an element and which doesn't affect your result. We say point at infinity or 0. Inverse is basically if you add, you will get 0, your negated number, your inverse. Commutativity says that a plus b should be equal to b plus a. So if you satisfy all of this, you will get a group, and these are all our basic things that we are using in elliptic curve. So I will now show you how we calculate point addition. So yeah, this is the most basic one, right? You want to add p to q, so you draw a line. The third intersection point is your result, but you have to negate it on y-axis. So yeah, the opposite side of it will be your result. So this is how we calculate addition on elliptic curves. So yeah, when we say addition, it's like maybe you can imagine like 3 plus 2. No, it's like a little bit different. You have to do some tangent operations. That's why we are in the second singularity one. I told that the tangent line is pretty important, right? Yeah, because you are using on the calculations. I will show you like here. As you can see, like directly we are using tangent here. If you want to add q to itself, which you know, aka doubling, you have to take the tangent line of it. The other intersection point will be your result, and of course you have to negate it on y-axis. So you will get, yeah, the minus p is your result. This is what we call doubling. Yeah, I'm going pretty fast though. Yeah, let's talk about negate. So if your Q is your you know, negate, like if you add 3 to -3, you will get 0, right? It's same on elliptic curves as well. This means you have to draw a line and it won't intersect any point, you know, and we call this as 0. As I told, 0 is our point at infinity in elliptic curves. So yeah, here P is point at infinity, the only point that on the left side, like the on the edge, it's our point at infinity. And if you add 0 to 0, which will never intersect any, you know, third point, so it's also point at infinity. So if you add 0 to 0, you will get 0. Basic, the same on the real numbers. So yeah. So yeah, scalar multiplication. This is a good algorithm. Actually, as I told you, like on private key to public key, for example, when we calculate this, we use scalar multiplication actually. So if you add p to p, you will get 2p, and add another p, you will get 3p, another 5p, you will get 8p, right? Like 8p, we have this 8 number on the, like near our p, or 11, for example, here in this example, like 11p. What we mean with 11p? It means that you have to add p 11 times to the result, right? You have a sum and you have to add p. So it's a lot of job. You have to do this like 11 times. And instead of doing this addition, we have this algorithm double and add, which is way easier, and it's cheaper than the original method, you know. What it says that if you have like 11 in front of your number, you can just convert it to bits, and if the right side, like the first bit, is 1, it means that take the p, put inside a bag, the sum, the bag is your sum, right? And keep it there. And look the second one. If it's 1, take double your p and add inside the bag. So you got 3p in your bag. And if the next one is 0, just double it, you get 4p, but don't put inside your bag. And the last one is 1, and double this 4p, it's 8p, and put inside your bag. So you will get 11p. This is the basic algorithm, and it's way cheaper to calculate like one by one. You can use this double. Double is way cheaper. So you can just calculate any number like this. So this will give us something new, and which is our scalar field. Scalar field. These scalar numbers in front of our p, 1, 2, 3, 4, 5. These are new numbers, right? And if they are prime number, prime q, we call this fq. This will be your scalar field. This will be your scalar field, and in some elliptic curves, scalar field is bigger than base field. In some, it's smaller. It depends. It changes. This is another thing. And most of the time, for example, your private case the private case are inside this scalar field, which is a random point. It's a very big field as well. And you are just taking this number and multiply it with your generator. Generator is a specific point on elliptic curve, and everyone multiplies their private key with this generator and gets the result, and it will be your public key, right? So this scalar field is where we keep our private keys. So yeah, this is basically how we calculate this big public, how people cannot find, right? This is because this multiplication, the scalar multiplication is pretty hard to, like discrete logarithm is pretty hard, because these numbers are very big, like 2 over 256. I googled it, I guess, like estimated number of atoms inside our universe is like 10 to the 80, something like this. And I guess 2 over 256 is like 10 to 82, something like this. So it's more than that. You can just pick random atom inside the universe. It will be your private number. No one can find it. So that's that hard. Yeah, let's talk a little bit about ZK proofs as well. I will just show some properties of it. I guess most of you guys heard about zero knowledge proofs before, and yeah, it's a proof that you can prove something without revealing any data to the verifier. They will just say, okay, I believe you. You're like, okay, you proved that. It's not believing, but yeah, you prove that you know the result of this equation, but they don't know your witness values, your secret values. So this is what we call ZK proofs. Okay, how do they work? We have to satisfy these three properties to call a proof a zero knowledge proof. Yeah, it has to satisfy completeness, which says that if your input is valid, you cannot your result always will be valid, right? You cannot create some invalid. It's nonsense, but you cannot create something false with correct values. And the soundness is the opposite of it, which says that it's theoretically impossible to return true with using wrong inputs. I said theoretically because, yeah, you can do it, but as I told you, it's like very hard. Like that's why theoretically impossible, but there's a still, very low chance, very low. So the zero knowledge part is why we call this proof zero knowledge, which states that verifier, they don't learn anything about your secret values. That means you have zero knowledge proof. Yeah, we have three different elements in zero knowledge. Actually, like all proofs. The first one is our witness. Witness values are your secret values, which you don't want to share with the verifier. You don't want them to know this. This is your solution. Challenge is the challenge that in most of the proof schemes, like verifier gives random, a challenge to the prover. So each verifier says that, okay, this guy has the correct witness values because they can solve my challenges. And the response is the response that prover accepts this challenge and gives back the solution to verifier, which we call is a response. In snarks, we don't have this. Challenge is the challenge is inside the prover's calculations, so they don't have to interact with each other, so they can just create their challenges and they can calculate the response. Verifier will accept that. That's why they don't have to talk each other, and verifier just takes the proof, just calculates and says, okay, you are good to go. They don't have to interact. So yeah, this is what we call snark. But yeah, it's not the topic, so yeah, thanks for listening. I hope it was good. Sorry for sliding a lot. Anyone? Question? I guess no one here. I can do it by myself. Yeah, let me bring the microphone.
Okay, thank you. First thing, you talk about groups, okay, and you mentioned then generator, and you multiply your private key with generator points. So I think that is important hint to mention cyclic groups. Okay.
Yeah.
Okay. Can you explain this? And of course, you mentioned and double algorithm, and this algorithm is not efficient. And maybe you can explain how, when we are using ZK provers, use different algorithms, MSM and so on, in order to obtain efficiency of the prover. Thank you.
Um, so I don't want to. Yeah, I can talk. Let me explain the MSM part. So yeah, multiscalar multiplication is more efficient. I didn't want to say that it's the best efficient one. Like it's better than the calculation, like one by one, like p plus p plus p, like it's 3p. Instead of this, you can use double and add algorithm, which will give you some efficiency, but it's not the most efficient one. You can use multiscalar multiplication. Actually, yeah, I coded that, but I'm not remembering the details. Let me think. So yeah, that's why that's why I am having some hard time. But you have some table. Yeah, I have to look into it and I can explain it to you, because like I'm not that prepared right now for it, but I don't want to give some false information to people. But yeah, I have some coding I can show. I did this before. I guess Onur, he's also Turkish. He's inside PAC as well. He has some good paper about this, MSM. You can check that, like batch multiplication as well. These are good methods. These are good algorithms that you can use in real life cases. Like I think these are the most efficient now. I am not sure. That's why I don't want to talk too much. But they are better than this double and add algorithm. Also for cyclic groups, I would like to, yeah, I can explain to you one by like face to face, because I don't want to give some fuzzy. I am not a mathematician, and if I say something wrong, it will be bad, I guess, in this case. As a developer, we use these papers. Mathematicians wrote this, and we are just using them to code. So yeah, I was. Thank you for the questions. Yeah, I will explain to you. Yeah. Oh, okay, then yeah, you explain, I code, so we can do that. But yeah, any other questions? I am always happy to try to answer at least. Why I am doing this is that if someone wants to be, I don't know, ZK developer, um, this is what happens, right? You don't have to know all the mathematics part, like you don't have to know all the details. You can just code these by asking mathematicians. You can just open papers, you can use them, and you can code your stuff, and it will work. And you will say, okay, this is, and you can do your own research, of course, like, okay, the batch multiplication or MSM, I don't know, like double and add algorithm, which one is like more efficient? You can use your like, I don't know, VSC to just see the results, and you can just compare it. I think this is why I'm trying to do this. If you want to be a ZK engineer, you can just learn these fundamental parts, and you can just go step by step and ask mathematicians. So I will ask her, and she will explain, I guess. We can talk it later. Yeah. Thank you.